Alright, silly people, here's the situation. Griffiths is going to have us solve this differential equation uh, that he already solved in the line preceding this problem. Um, so we're just going to be filling in the gaps of how he even did it. So this is kind of interesting since I don't really get to solve a lot of differential equations on this channel in this textbook. So it's a unique opportunity here. Uh, so what I'm doing right now is I'm just moving the stuff which depends on just psi to the right hand side of the equation, and then keeping the stuff which depends on the derivative of psi on the left. Um, and then I'm just going to do a little bit more algebra, moving the minus I h bar to the other side. That will coalesce into minus, or plus actually, I over h bar times this stuff inside the brackets here, if you like. And then I'm going to go ahead and also factor out the A thing. So, everything that depends on A. So we got A over h bar, and then I'm going to factor through the I that's on the outside. So I'll have 1 over A, the expectation value of P, and it's I over A actually, minus just X minus expectation value of X. And then we can distribute that minus sign through as well. So that's I expectation value of P over A minus X plus expectation value of X is equal to psi. Or, yeah, that's what it is. Acting on psi. Okay. Now, I'm going to move the psi to the other side, and then move the dx to the other side. So I'm just saying now I'm doing d psi over psi equals a over h bar I expectation value of p over a minus x plus expectation value of x dx, and then I'm going to just integrate both sides now. On the left hand side, integrating with respect to psi. On the right hand side, integrating with respect to x. So you just got natural log of psi on the left hand side. And on the right hand side, it's a over h bar in brackets I expectation value of p over a times x minus x squared over 2 plus expectation value of x times x plus c. If you remember from Calculus 1, you remember how embarrassing it is to forget the plus c, so don't do it here. Because this isn't a definite integral here. So what we're going to do now is I'm actually going to try and complete the square. You notice I have minus x squared over 2 plus expectation value of x times x. What's missing is expectation value of x squared over 2. So let's just add that piece inside the brackets and subtract it outside the brackets. So we have minus x squared over 2 plus expectation value of x times x minus expectation value of x squared over 2 inside the brackets plus c, and then we'll also have to add on plus a expectation value of x squared over 2 h bar on the outside, because we completed the square pretty much. The cool thing is, though, is that the expectation value of x is a constant in this equation, so ergo we don't actually have to include it explicitly in the form of the solution. We can just lump it up into the constant that is c. So I'm going to call a new constant c plus a expectation value of x squared over 2h bar. I'm just going to call that constant b. So no longer a differential equation, but our just equation now reads natural log of psi a over h bar I expectation value p over a x minus, and then I'm going to go ahead and collect this into 1/2 of x minus expectation value of x squared, and then plus b on the outside. Right? Yeah. Okay. Now the next logical step is to raise both sides to the e, so we can have psi of x as a function. So it's e, and I'm going to leave it as an exponent for now just because things are still kind of gross. But it's a over h bar bracket I expectation value of p over a x minus 1/2 x minus expectation value of x squared, close bracket, close curly brackets, and then out here we have e to the b, which we can call our normalization factor a, which is how Griffiths got the form that he did in the textbook. So I'm just calling, again, b is a constant, so I can just call it whatever I want. E to the b is a new constant, which is a. And then after that we have a, e, and then I'm going to try and separate stuff out a little bit now. I expectation value of p x over h bar, yeah, and then e to the minus a times x expectation value of x squared over 2h bar. And I think that's the way that Griffiths left it in the book. Yeah, it is. Okay.